Hello, kids. This is Mr. Joseph, and I'm going to give you an introduction to nuclear chemistry today. And so, nuclear chemistry has to deal with the nucleus of an atom, and these are called nuclides. So, if we look at a nucleus of an atom, let's do the simplest atom, which would be a proton. That's a nucleus of a hydrogen atom. That's a very stable atom with our stable nucleus. If we add two neutrons, though, these are two neutrons, right? These are, this is hydrogen 1, this is hydrogen 2, or 3. This is unstable. And the nucleus itself will fall apart eventually. And to describe atoms and their stability, you can take the ratio of their protons and neutrons, and I'm going to put a picture here. It's called the belt of stability, where the atoms are stable inside of this range when the number of protons is, say, 50 and 70 neutrons. That would be a stable atom. And then if it falls outside of that, then you're going to have an unstable atom, and the particles will decay by nuclear means. So let's look at some ways that we can have some nuclear decay. That is, the nucleus of the atom is falling apart and forming different types of atoms. So here's a picture. I'm going to show you another picture. You have access to these pictures in another document that I am providing to you. Oh, that's not what I wanted. Why is it not? Here we have a radioactive substance in a lead block, and with a hole in it, it only allows the radioactive stuff from it as it falls apart to come out of in one direction. And if it goes through two charged plates, you can see these things called beta particles go up toward the positive, which means they must have a charge of what? Yes, negative. And if you have these alpha particles that go down toward the negative, they must be charged positively. And you can see that the beta particles are deflected more easily, and that means that they are lighter, and the alpha particles are deflected not as much, and so that means they are heavier, they have more mass. These gamma rays are just electromagnetic rays, very high energy rays, and they don't have any charge at all, so they aren't affected by the charged plates. Let's take a look at another thing here. So here's a table that represents some of these items. An alpha particle, again, has a charge of 2. There's the mass. The beta particle has negative charge. And these cannot get through items and cause damage into your skin or whatnot. That's what that means by the penetrating power. We're going to use our reference tables next for some of these types of particles that come off of radioactive substances. And so reference table O is going to come in handy. And here's our alpha particle again. And the notation, you have your mass number, 4, and the atomic number 2. This is just the nucleus of a helium atom, and so you can use helium, or you can use the symbol for alpha, which is this particle right here. We're going to go through and we're going to figure out what types of radiation occurs from different types of substances. Okay? So there are 3 types of radiation that we're going to talk about. These are called natural transmutations. Natural transmutations occur when you have an unstable nucleus. Oh, man. When you have an unstable nucleus and it will decay, the nucleus will decay into something else. So we're going to talk about alpha decay. We're going to talk about beta decay. And we're going to talk about positron emission. Those are the three that we will talk about. Now, how do we know which type of transmutation will occur in an atom? And that would be answered by looking at table N. In table N, we can see an alpha decay for this francium right here. So let's go ahead and write out the alpha decay for francium. What would happen if francium were to decay? And we start with the beginning, which is a francium atom, a nuclide, right? And this would be a nuclide with 220 particles in the center. And francium itself, we need to look on the periodic table and see what the atomic number is for it, because that's important to describing these nuclear decays. And it turns out francium has 87 protons. That's its atomic number. All right, and now it's decaying, so it's going to go afterward. So this is the before. Afterward, it's going to have an alpha particle, and we know that because of this decay mode, alpha particle. Let's go to our chart and see what the symbol is for an alpha particle. Alpha particle looks like this, 4, 2. So we're going to write that because that's what's going to come out of the francium, 4, 2. All right. So afterward, we're going to have 4. 2 of them are going to be positive. They're the protons. And there will be some things left over because obviously you can't have items disappear. And there were 220 things in that nucleus before. So what's left over? There should be how many items left? Well, we took 4 out of them. So that means that there should be 216, right? Oops. So there'd be 216, and some of these particles in here obviously are positive. I didn't write them all in there. It's hard to do that. And there's a whole bunch of these. And how many protons are there going to be? We took 2 protons out. We started with 87, so they're going to be 85. And because of that, which element is now that a nucleus of? And if we go and look at the 85 on the periodic table, which you should, then that is going to be AT. And that is our alpha decay equation. And that's how something that decays by alpha decay, because it has an unstable nucleus, how it occurs, right? So in other words, if we had in this little block, if this was francium, what would come out of this? It would be alpha particles, and you would see them come down like this, right? This shows 3 streams, but really only 1 stream would occur at a time, depending on what you put inside the lead block. Okay, so we did alpha decay. Let's do beta decay next. And we will get our table N. Actually, let's just make a copy of this. And then we'll erase our other things. All right, so now we're going to do a beta decay. I'm going to leave a large nuclide right there. So what one is a beta decay? So we have these B minuses, and we have these B pluses, right? Oh, come on. Come on, come on. Oh, I changed the wrong one. Let's move it over here. There we go. Okay, so we have our B minuses and our B pluses. Which one is the beta? Well, a beta is actually just an electron. And from our table O, we can see the beta particle looks like this, and it's a B minus. And so we're going to use the B minus when we do this. So let's choose one of these as the B minus. Let me duplicate this for our last one as well. And then we will be good to go. Okay. All right. So we're choosing a B minus this time for a beta decay. Let's use the, how about we use the carbon 14? All right, actually that's going to be a much smaller nuclide, so I can go ahead and write out that nuclide. Carbon 14, we know carbon has 6 protons from the periodic table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. 8 neutrons, because that needs to add up to 14. So C14, 6, and it's going to decay. And what's going to come out of that carbon? That radioactive carbon. And why is it radioactive? Again, it's because the nucleus is not stable. It does not rest in the belt of stability that's shown right here. Carbon 14 would be out of this stability, and it would be radioactive and fall apart. So if we put it into the lead block, it's going to spit out beta particles, which would then move along that path. And so for our beta decay, it's spitting out the beta particles. The beta particle is just an electron, like this. There's actually no protons or anything changing. There's no protons changing. So they're still going to, no, yes, protons are changing. The total number of particles is not changing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. However, as we'll see with this particle that has no mass, has a negative charge, we're going to, oh, I totally botched that. Has no mass, has a negative charge. So what plus -1 equals 6? Well, that would be 7. So we have 7 here, we have 14 here, and that means there's 7 protons. 1, 2, 3, 4, 5, 6, 7. What has 7 protons? Look on your periodic table, and you'll see that it is nitrogen. So nitrogen is there. And what happened here exactly? Well, a neutron turned into a proton, and in the process, it spit out an electron. So the neutron, a neutron that has no mass, has 1 mass and no charge, became an electron and a proton, like this. That's what really happened inside that. So this is a beta decay. Okay? And finally, our final one we're going to look at is positron emission. It's our third one. Positron emission. What is a positron? Well, a positron is a positive electron. It's a particle that we really haven't talked about, but they do exist. There's some really funky particles out there. And so this would be a positron right here. The iron emits a positron. And so we're going to start with that nuclide of iron. 53, again, unstable because it cannot stay together. It has a bad ratio of neutrons to protons. It won't be stable. So 53, we're going to put 26 down here because that's our atomic number. it's going to spit out a positron. This time I'm going to draw it like this, and you can go to table O and see that's the case. It's a plus charge and no mass. Why do I keep doing that? It's the opposite. Come on, Mr. Josephs. So you can think of this bottom number as not just the number of nuclei of protons, but it's also the charge. So, right, because protons are charged, +1. So this is a positive electron. It doesn't have any mass, but it does have a charge. And so what plus 1 equals 26? Well, that'd be 25. And 53 plus 0 is 53. So that's what we do there. And we can see that the symbol will be Mn. It's manganese, I believe. And so down here, I'm just going to write B minus plus. Then you've got all these in here. This is the manganese nucleus. All right. Here are two more examples of an alpha decay and another example of a beta decay. This alpha decay, you can see that you've got you can see that Ra is alpha decay on table N of your reference tables. And this one is not listed on your reference tables because there are obviously more things that are radioactive and giving off different types of decays than are listed on table N. But there's another example for you. You've got some questions to answer in Google slides that I made for you, along with all this information that's included. And also there's another another assignment in which you have to make a trifold pamphlet, and you'll be working on that today and tomorrow for this week. All right, and this topic. All right, have a good day, guys. Bye-bye.